Discussion board question. All right. That would require me to be logged into Blackboard now, wouldn't it? All right, just so those of you can see it later on, the discussion board here that we're being asked about is this question. So, given to 2 decimal points, what is the pH of a solution? Of a 0.1 molar carbonate solution. Given that the pKb is 3.67. So, basic problems represent the hardest end of the acid-base problems because they basically require you to kind of go attack something that you don't attack for the acidic problems. So for the acidic problems, the pH is easily solved because you're always solving for the H plus concentration. The complication with working under basic conditions is that instead of going directly for the pH, you're actually going to try to target the pOH first. So for these basic problems, don't answer the pH question, answer the pOH question, because we know the pH is just 14 minus the pOH. Now also, we're almost exclusively going to work with Bronston bases. These are the ones that are the proton acceptors. So you're given a 0.1 molar carbonate solution. Carbonate is CO3 minus 2. So if we add water to act like a base, it's going to accept the hydrogen. So this gives us bicarbonate. So this is our reaction. But again, this is like pretty much all equilibrium problems. If we want to answer the question, we've got to have 3 components. We've got to have our expression for KQ. In this case, because it's a base, it's a KB. This is going to be equal to Q at equilibrium. So it's going to be in equilibrium concentration of HCO3 minus 1 bicarbonate, concentration of hydroxide over the concentration of carbonate. And we have to have our IC table. Initial concentration of the carbonate given to us is 0.1 molar. We're going to assume the hydroxide is 0, that nothing comes from the water. And we're not giving a concentration of bicarbonate, so that's 0 molar. Changes are minus X, X, and X. In value, 0.1 minus X, X, and X. And again, we're being asked for the pH, but with the basic problems, this is actually, pH is going to be what you get to in a roundabout way. For basic problems, you actually want to go for the pOH first. And our pOH is just going to be the negative log of our hydroxide concentrations. This is the part of the IC table we're going to target. So, building back on previous equilibrium problems, we know Kb, it's 10 to the negative 3.67. We know the equilibrium values, it's X, X all over 0.1 minus X. So we get, when we rearrange it, X squared plus KBX minus 0.1 KB equals 0. When we solve for X, we will get a number. The negative log of X is our pOH. So our pH is just 14 minus that number. So that's how you approach the discussion board today. Since your test is Monday, I say the hardest question for last. You are going to have a basic problem on the exam. You're going to be asked to figure out the pH base underneath a basic solution. But hopefully what you can see here is that it's pretty much everything you've already done so far. The 2 major differences, one, it's a base now, so instead of losing a hydrogen, it's going to gain a hydrogen. The second is that we want the pH ultimately, but that's not what we're going to go after. What we're going to go after is the OH minus, because that gives us the pOH, and from your Blair diagrams, they get you back to the pH. That help you out, Mohammed? Yeah, basic problems represent the hardest extreme of these acid-base problems. Acid problems are easy to work with because we measure pH, so it's just converting between H plus and pH. Here the challenge is that we're actually solving for OH minus. But again, our Blair diagram, once we know one corner on it, we know the other three corners as well. Can you do that within an IC table? No. There are ways. If I gave you a basic buffer, we can try and work it if you want. There is a Henderson Hasselbach equivalent for a basic buffer. So if I gave you carbonate and bicarbonate, let's back up. So this is the Henderson-Hasselbach equation. So let's say we had spitting out a domain error. Odds are that where you've got the +4, or you've got the -4 times AC in your quadratic, back it up. So odds are if you're getting an error in terms of domain, your C term in the quadratic equation, so x squared plus bx plus c, remember that this is minus kb times 0.1. It's not kb times 0.1. That negative will flip the sign of the quadratic, so odds are that domain error is because you've ended up with an imaginary number. Now, for Henderson-Hasselbach, we do have an equivalent. This comes from the expression that Ka is concentration of H plus A minus all over HA. We can play the same thing with Kb. Let's do B's. And when we rearrange, we get PKB equals the POH equals the PKB plus the log, the concentration of the conjugate base over the concentration of the base. And using the relationship that pH equals 14 minus POH, we can rearrange. So we get 14 minus pH equals PKV plus the log HB over B. This is kind of unwieldy to work with. There's a lot of algebraic rearrangements to work with, but again, this is only going to work if you have a basic buffer. In the case of the one we're given with the carbonate, we can't use this relationship at all because we don't have any conjugate acid. Same thing's true with Henderson-Hasselbach when it comes to acidic conditions. If you have acidic conditions, an acidic buffer, and assuming your concentrations are high enough, you can still work with the Henderson-Hasselbach equation. It's much faster. But if you're given an acid, something like acetic acid with no conjugate acetate, you can't use the Henderson-Hasselbach, so you have to build an IC table. Is there any discussion, any practice on deriving the reaction like you did for the discussion board? Kind of, that's where the, so if you look at the fronts of the packets, it asks you to define what a Bronsted acid is, what an Arrhenius acid is. It asks you to identify conjugate acids and bases. That's all kind of building on this idea. But, so with any acidic reaction, pretty much for this level of chemistry, we're going to stick to Bronsted definitions of acids and bases. If you go into organic, you're going to follow a lot more with Lewis definitions, and for the rest of chemistry, it just depends on what you're taking. But the Bronsted definition of the acid is going to be this. the Bronston definition of the base is going to be this. So if you're ever working underneath acidic conditions, your acid is going to be the one with more hydrogens. The conjugate base is going to be whatever's with less. So in the case of acetic acid, HC2, H3O2, it acts like an acid by losing a hydrogen. And this will be true for all acid-base reactions. The acid loses a hydrogen. If you're given a basic condition, in the case of carbonate, this is going to be our base. We're still going to have water in there. We're still going to form the OH minus. Our conjugate base is the base plus a hydrogen. So HCO3 minus 1. So I don't really have practice for you because it's just kind of the practice was kind of there at the beginning to say, do you know what define what they are, identify the acids and the bases, and hopefully by identifying the acids and bases and the conjugate acids and conjugate bases, you start picking up on these relationships. The challenge kind of at this level of chemistry, particularly with chemistry 2, is no longer thinking about things as specific examples, but thinking them as broad classes. So we have acids. This is how all acids act. Here's a specific example. For bases, this is how all our bases are going to act, and this is a specific example. So to get you out of the mindset of memorizing each particular case and saying, well, if I have an acid, I know it has to do this, so I just need to see what my specific example is and make it look like this. Same thing's true of your base. Just make it look like that. And again, there's no gotchas with these. I'm going to say, like, this is a basic situation, this is an acidic situation, or it's going to be strongly applied. If I give you a Ka, it's acidic. If I give you a Kb, it's basic. In principle, I could give you the Ka of a weak base. You could backtrack out the Kb. There is a formula for that. I don't think that's necessarily useful for you to do. At this level, your ability to do this and solve these problems is much more useful. Now, as I said in the previous video, and I'm going to reiterate here, please, when the exam opens up next Monday, go ahead and start it. Wednesday, we're going to start on redox. Those of you who had me for Chem 1 know redox is intense. Those of you who did not have me for Chem 1, I assure you, redox is intense. I'm guessing a lot of you are going to show up next Wednesday to ask me questions. It's hard, so go ahead and get your exam out of the way so you're not having to master redox at the same time you're trying to get assessed on how to do acid-based stuff. I personally think your fourth exam is the easiest. Historically, this has been the one that most people pass. How many people showed up today? Let's see. You should be getting a positive number for X, so check the roots. The nice thing about acid base, we're always going to go with the positive root because the extended reaction X is always going to equal the concentration of the H plus or the OH minus. Because of that, we always have to end up with a positive root. But for you're having specific problems, shoot me an email. It's a little bit easier to work through this with an email and a text editor than it is to try to do it through the discussion board on YouTube chat. So that is the PKP value of 3.76, but that is not the KB. So KB and PKB are not the same thing. They're related the same way pH is related to POH. So to make it a little bit clearer, you got your Blair diagram, pH, H plus, POH, and OH minus. The connection between these two is that Kw equals concentration of H plus times concentration of OH minus. 14 equals pH plus POH. And here we have the connection that pH is a negative log of H plus, and POH is the negative log of OH minus. There's actually an analogous relationship with Ka and Kb. So I'm writing this intentionally small. I know it's going to be hard to view, but you should already have a copy of this in your Blair diagrams. So the Ka-Kb equivalent here, pKa, pKb, Ka, and Kb. So the pKa is just the negative log of Ka, and the same thing's true of the pKb. The pKb equals the negative log of Kb. These two are connected by 14 equals pKa plus pKb, and these are connected that the Ka times the Kb equals Kw. So if you take your Blair diagram and instead of doing H plus and pH and OH minus and OH minus, or POH, do the same things for your Ka. So your pKa is the negative log of the Ka. Your pKb is the negative log of Kb. So in your expression for equilibrium, it's not pKb equals Q. That's not a true statement. It's Kb equals Q. So if you're given pKa or pKb, you have to back convert into Ka and Kb. The reason we prefer to work in pKas and pKbs is that it's just easier to handle them. If you look at what Ka and Kb are, they are something times 10 to the negative something. So for simplicity and ease of tables, we keep it in terms of p's, knowing that we'd have to backtrack it out. So your 3.7 isn't what you're going to work with. Your Kb here is 10 to the minus 3.67. Because the other thing to keep in mind, these are weak acids and bases. Now, I'm going to contradict myself here, but understand that typically when we work with something like a 0.1 to 1 molar solution, with a weak acid, weak base, we're typically sticking in the 3 to 10 pH range. Now, they can get super basic if we have high concentrations, but we're not working with them. So if you're doing these calculations and you're getting like a POH of 1, go back and make sure you're working with the Kb and not the pKb. Same thing's true with the Ka and the pK. If you're doing the pH of a weak acid and you're getting like a pH of 1, odds are you use the pKa and not the Ka. Can I post the answer I got in the chat? You can. I'm not sure what the answer for the discussion board is off the top of my head, though. I mean, about what were you getting? Because I think the pH is like 11 or 12 or something like that. And honestly, if you want to, just post it in the discussion board. If you go back and look through your discussion board post, if you haven't gotten a grade immediately, go back and see if I've replied to your post. Odds are I'll post in there saying, hey, you didn't quite do this right, to give you another chance to do it. The goal here is not to penalize you for being wrong. The goal is to make sure you understand that. So if you get like a grade of 6 and you go back and go, oh, this was my mistake, and you go back and correct it, I'll see on my end that you've recorrected it, and I'll redo your score. Oh, let's see what other people got. So Mohammed, we'll come back to your question, just because it's going to require me to work with Excel. Actually, no, I'll tell you what, let me go ahead and answer that question really quick about what the POH would be. So I've got a PKB. So I'm going to have to work this off screen. So my PKB is 3.76. Then my KB, which is 10 to the negative of that number. Now, my root is going to be the opposite of KB. We're going to go with the positive root, square root, KB squared, 4 times KB times the starting concentration, which is 0.1, all of that divided by 2. So where that comes from, we'll switch back to the whiteboard really quick. Where that comes from, we get the x squared equals kb, x squared over 0.1 minus x equals kb. So we get x squared plus kbx minus 0.1 kb equals 0, quadratic equation. So kb plus kb squared plus, and it's going to be a plus here because of the negative, 4 times 0.1 times kb all over 2. So this is what my x value ends up being, which is coincidentally, well, not coincidentally, we know it's the concentration of OH minus. So the POH here is just the negative log of that number. So I get 2.3839 for the POH. The pH is just 14 minus that number. So pH here is going to be 11.6. The POH is going to be 2.4. Now, in terms of the homework, yeah, in terms of rounding, you're going to find that a lot. Problems on the test are generally reserved for problems where they're not sensitive to how the load precision of your calculators. Homework, I got a whole bunch of other examples left over, and I know you can do those in Excel. So let me bring up Kyle's question. About the WebAssign. So many good questions in this one. Okay, so let's make sure you understand the one about the buffers first. So I'll keep your chat up here to the side, just so I can see it. Now, in terms of what makes a buffer, it always has to be a weak acid in its conjugate base or a weak base in its conjugate acid. So what you can see with this one, the first one, H2SO4 and NaHSO4, not a buffer because H2SO4 is one of your 7 strong acids. CaCl2 and ACl, neither of those are acids. HCl is a strong acid, so process of limit is H2SO3, but if we backtrack, H2SO3 is a weak base, or a weak acid. Its conjugate is going to be something bound to HSO3, because when H2SO3 acts like an acid, bring it back up. So if we have H2SO3 as a weak acid, its conjugate base is going to be that minus a hydrogen. So our weak acid expression is always this. So there's our A minus, our conjugate base. There's our parent acid, H2SO3. So a buffer is going to be anything that's our parent acid minus a hydrogen. Now we can't buy bisulfite off a shelf. So what you're generally going to see these paired with is something like NaHSO3 or Li or CS or rubidium, something that is soluble in water. So the solubility questions here are just making sure you're picking up on that. So in terms of this one, which compound is most likely a solid in solution? Well, this is just where you're going to go back to your solubility rules, and the whole point for having questions 3 and 4 here is just to make sure that you understand what doesn't make sense in terms of a conjugate base. So if you want to make a buffer, you don't want to add anything that doesn't dissolve in water. So our first example, magnesium sulfite. MgSO3 plus sodium chloride goes to sodium sulfite plus magnesium chloride, MgCl2. So the question is, what's solid in this? Well, we talked about, for the last exam, the solubility rules and the insolubility rules. So the easiest one to do is go through and do the solubility rules. We're going to kind of cheat. We know that one of these is insoluble, so it's probably going to be the one that doesn't have a solubility rule associated with it. Your solubility rules, anything bound to a column 1 metal, so lithium, sodium, potassium, rubidium, cesium, francium, all of those are soluble in water. Anything bound to ammonium, NH4+, soluble in water. Anything bound to nitrate, soluble in water. Chlorite, ClO3, soluble in water. Sulfate, except for calcium, barium, strontium, are soluble in water. Also, silver, lead, and I think it's mercury. Yeah, mercury sulfate. Chlorine, iodine, bromine, those are all soluble with the exception of lead, silver, and mercury. So if we look through here, magnesium does not have a solubility rule. Sulfite does not have a solubility rule. So this is most likely the solid complex, but let's keep going. Sodium chloride, sodium has a solubility rule. So anything with sodium in it is soluble in water. So that's got to be aqueous. Chloride, anything bound to that except for lead, silver, or mercury, soluble in water. So that's definitely aqueous on this side. It's just magnesium and sulfite we don't have a solubility rule for. And because of that, since we don't have a solubility rule, we're going to assume that these are insoluble. Now, the exam is not going to focus heavily on this. Again, it's mostly what I've noticed with students is that they picked any ion to go along with their conjugate base or their conjugate acid when they were doing these problems. This is just to remind you, you need to pick, when you pick something to make a conjugate base or a conjugate acid to make a buffer, make sure it's actually soluble in water. If it's not going to accomplish anything. So yeah, for your conjugate bases, make sure it's bound to something in the first column other than ammonium. If you're making a conjugate acid, probably kind of the same rules actually. What other questions you got for me? Okay, so we've got a question from Elijah. pH of a basic buffer solution. And we've got 0.3 molar. Na2HBO4. The other one is 0.025. NaH2PO4. And according to him, it's page 13 on the handout sheet. So, again, once you start saying you're under basic conditions, this is the end, but this is how we're going to get there, is through the POH. Now, again, you can go back to the lower diagram, you can actually go from OH minus to H plus pH. Much easier to go for the POH. So once you say you're under a basic condition, start shooting for the POH. Now, for your convenience, I always list the base and the conjugate. Base first, conjugate second. Same thing you've probably seen with the acids. I list the acid first and the conjugate second. The way you would know that this is the conjugate, if it's a base, it's going to accept a hydrogen, which means it's going to gain an H. So since this has more hydrogens, this is the conjugate of this. But we have HPO4 minus 2. Our form of all bases is our base plus water. Goes back and forth to HB plus OH minus. Now this plus here just means that it's going to gain a +1 charge. In this case, we start with a -2. We're going to gain a hydrogen. So this will give us H2PO4 minus 1. So that's our base. That's our conjugate acid. Instead of working with Ka, we're going to work with Kb. It's just equal to Q. Q in this case is OH minus. H2PO4 minus 1 all over HPO4 minus 2. So you've got your Q equals KQ. Last thing you need is your IC table. So you're almost there. We've got our starting concentration, 0.30, 0.0250 minus X, X and X, so 0.3 minus X, X and 0.0250 plus X. We're going to stick this row into this expression, so we get X times X plus 0.0250 all over 0.3 minus X. Again, keep in mind you're given the PKB, not the KB. So if your PKB here is 6.80, your KB is just 10 to the minus 6.80. So At this point, you're back to solving a quadratic. You would rearrange this quadratic equation. So, just kind of ignore this part. KB equals all this. Solve for x. X will give you the OH minus concentration. The OH minus concentration, just take the negative log of that. That'll give you your POH. And then your pH is just 14 minus the POH. So, that help you out? Nobody's not seeing it, so let me see if I can find it really quick. So to answer Abby's question, if you go to the packets, pH from PKB, basic buffer, that is 0.2 molar Na2HBO4 and 0.025 molar NaH2PO4. So this is the problem we're talking about here. And it is on page 13 of the packets, and it is the last problem on that page. Looks like I didn't show it to you. So it's this page, pH from PKB, this problem. Your lab practical is actually the last week class. It'll be the first full week in May, and it will be deployed online. You will have all week to take it. It was the lab practical practice that had been up there for a while. I just took it out and cleared out all the grades. If you already did it, congratulations, you've seen what the questions are going to be, but your grade's been reset. But that's what the lab practical is going to be this semester. You can take it at any time. It's going to be like any exam. You get 2 hours and 50 minutes to take it. That said, it definitely does not take 2 hours and 50 minutes to take that. So I think it's like 8 questions or 9 questions. The week before, I will post what the specific topics are going to be on it. So this way you can see what's happening. So you know what to look for. But this practical is not meant to be like a gotcha practical. Like, there's a question there on Beer's Law. There's a question on what concepts are supposed to be covered in what lab. There's questions about how to read a titration curve, things like that. So honestly, you should be fine. I say hopefully. But, there's nothing on this exam, there's nothing on the lab practical that should be completely out of left field. And you have all your resources at your disposal to take it. Yeah, I kind of hope by this point in the semester, like equilibrium, because we spent a ton of time on equilibrium. It's all kind of clicked to you at this point that it's really an IC table, an equilibrium expression, and that's it. Everything beyond here is just like extra work. But hopefully at this point, like, you've really got the concept of equilibrium down. And equilibrium will show up for electrochem. Electrochemical reactions are all treated as if they are reversible reactions, which has a massive impact on how they work. But yeah, equilibrium is like 40 to 50% of the material we covered in Chem 2. And I'm hoping at this point you're like, oh, okay, what your struggles with are more where to put the information, not how to actually set up the problem. Okay, so what's not clicking with you, Elijah? Yeah, I asked that question and there's like a 15-second lag in these videos. Okay, so understanding what goes where. So let's look at the big envelope of acid-base problems. So with acid-base problems, we can split them into two categories. Acids and bases. And the real distinction between acids and bases is simply what reaction we're looking at. If we're looking at an acidic reaction, HA goes back and forth to H plus and A minus. If it's a basic reaction, it's B plus H2O, goes back and forth to BH plus and OH minus. So this is the really only significant difference between So the reaction is really the only significance in how we approach the problems because it's going to change our expressions for Q. In cases of acids, we're still going to have Ka equals Q in our expression for Q. For bases, it's still going to be Kb equals Q. We're still going to have our IC table. In this case, it's going to be the parent acid, H plus, and the conjugate base. And for the base scenario, it's going to be the base, the hydroxide, and the conjugate acid. And you've still got your IC table. Now, your first row, your I row, are all initial. So typically they're what's given to you. So, oh, if you're given this, if you're given this, you're given this. Your E row is where your pH, your POH, your H plus, and your OH minus are all going to show up. So if you're being asked to solve for pH, that's the equilibrium row. If you're being asked to solve for POH, that's the equilibrium row. Now I write all four of these because they're connected by that Blair diagram. So once we know the H plus or the OH minus, we uniquely define the other three parts of pH, POH, H plus, and OH minus. Now, this is a lot easier than the previous test for equilibrium problems because I could say, oh, equilibrium concentration, what's the starting concentration, things like that. The concentrations for our acids and bases are all going to be referring to the initials, specifically for acids and bases, and there's a reason for that. Practically, we don't care how much conjugate base is in there. We don't care how much acid remains at equilibrium because we're not measuring that. We're measuring the pH. So really, when we say concentrations with acid bases, where you're almost always referring to their initial concentrations, recognizing that their initial concentrations aren't their actual concentrations, but you can kind of see with pH, right? When you convert that to H plus, it's a teeny tiny number, unless it's like a really high pH. So our concentrations don't change that significantly. That is a good question, Abby. So is your issue just more just solving the quadratic equation? Okay. So let's just take a step back now. Chemistry is one concept, math is another. So math is a language. It's a quantitative language. And the trick with math is realizing that the reason we have to use it is that we speak English. English is a very qualitative language. So if I sit back and say it's raining outside, that doesn't tell you how much rain is coming down. Now I can allude to it. I can say it's a deluge. I can say it's sprinkling, it's pouring, something like that. It still doesn't quantify you. But if I say there's an inch coming down every hour, that quantifies it for you. So the trick with mathematics is keeping in mind what the variables stand for in the English language and just manipulating them in the math language. So generally when we do an acid-base problem, we'll get something like this. Ka equals x times 0.0250 plus x all over 0.3 minus x. So this is just a mathematical expression. Ka here is our equilibrium constant, x is our extent of reaction. So x describes how far the reaction went. X here, for our previous example, was the concentration of H+, concentration of the conjugate base. I'm sorry, I'm referring back to an older problem. I think this was the H2. Sorry, that was the base. Okay, let me really confuse you here. So we're just saying that the concentration of hydroxide is just the extent of reaction. And again, this is just a translation. We know from our IC table that they have to equal each other. So we're just translating into it. In terms of how you actually solve it, I personally like to leave the numbers out. And the reason I like to leave the numbers out is that it keeps me from having to keep track of all the numbers. So if I'm going to work algebraically, I want to work purely algebraically. I don't want to have any numbers substituted in there. So let's just keep that A is 0.0250. Let's keep B as 0.3. It's all a balance. So this is a scale balance. What it means is that if I put these on a scale, KB would weigh just as much as all these variables put together. So if I move it, if I take it off one side, I have to put it on the other. So to get rid of division, I just undo the operation. Undo division, I just multiply. So if I want to undo this, I multiply the whole thing times B minus X. So I get KB whole thing times B minus X equals X times A plus X over B minus X times B minus X. Now, the right side, the whole intent was to get rid of that B minus X in the denominator. So that's what I did. Now, the idea here is to isolate X. So to isolate X, I don't want any more multiplication left. I want to get it all in terms of addition and subtraction. So try to get rid of the multiplication division first. So if I distribute, multiply everything on the inside by everything on the outside to get B times KB minus X times B equals X times A plus X times itself is X squared. Now I want it all on one side, so I get 0 X squared plus X times A. I'll bring that term over. When I bring it over, I invert the signs. Let's get B times X. And when, again, I bring this over, it's going to be the opposite, minus B, KB. Group like terms. And now I have it set up for the quadratic equation. So the quadratic equation says that if I have AX squared plus bx plus c, x equals opposite of b plus or minus the square root b squared minus 4 ac all over 2a. A here is 1. B is a plus b, in this case 0.025 plus 0.3. And c here is the negative of b, 0.3 times the kb. So if the numbers are what's kind of throwing you off, like having numbers in there, work purely symbolically. Particularly with me, you'll notice I like to get rid of the numbers and just keep it symbolic until the very end. And then that's when I'll actually start putting it into the calculator and start putting numbers in. Now, in terms of what you do with the numbers, this is where the IC table is really nice. It kind of keeps you from losing the forest and the trees. So you go through all this work to find x. And generally what's happening is you're solving for x because it's the only thing you don't know in your IC table. So let's say we have an acid. We have HA, H plus, and A minus. And let's say they both start with 0, and this is 0.1. Change here. It's minus x, x and x. So I get 0.1 minus x, x and x. If I'm being asked to find the pH, I know the H plus and the pH are connected. So I know that this is the square I'm solving for. So once you do all this menagerie of work, the whole reason you're doing it was because you needed x to figure out what the concentration of H plus was. So once you solve for x, take a step back, look back at your IC table and try to figure out what you needed. You know, this is why I teach the IC table so hard for these equilibrium problems, is you can't lose, you can go through all this work and go, oh, I solved x. Well, x was a means to an end. You're welcome. It's kind of hard for me to actually take a step back. I've taken all the way through graduate mathematics, so for me, this is just a language sitting on the back of the board that I understand very well. It's very hard for me to slow down and explain it. The same way it would be hard for you to basically teach someone who's not an English speaker how to understand English. Like, you try to take small steps, but inherently you're going to use English to explain English. Same thing's true for math, is that for me, this makes a ton of sense, but I speak it very fluently. So please ask questions. Like, it's just very hard for me to remember a day when I didn't know like calculus and advanced calculus and the fields beyond calculus. And again, that's not to disparage y'all for your level of math. Like, there was a time in my life where I didn't know calculus. Now, if you are trying to learn math, I will say from my experience, maybe not from everyone's experience, it's like learning a sport. You don't get good working at your level, you get good working at a level above where you are. So if you're struggling with algebra, try to see what you can do with the next level up. And that's where I learned a lot about algebra because of trigonometry. I learned a lot about calculus because of trigonometry and so forth. So the question is, what method do we use to determine the formula for the discussion question? So the big thing here is how bases always act. So we have two general forms. We have the acid and the base equations. And this is why I make you memorize the definition of Bronsted acids and bases and Arrhenius Bronsted acids and bases. So for an acid, the general reaction is HA goes back and forth to H plus and A minus, and with the base, the general form is B plus H2O goes back and forth to BH plus and OH minus. So if it says acidic, you will have a reaction that looks like this. If it says basic, you will have a reaction like this. Now, as a favor to y'all, just because you are still learning this, I always list the acid and the conjugate base in that order. So the acid comes first, the conjugate base comes next. With the bases, I'm going to list the base first and the conjugate acid second, just to kind of keep you from having to figure that out. But if you're given something like, see, what was the reaction this time? Carbonic acid. Well, we had carbonate. So carbonate to base, it's going to go here. Water is always in this reaction. Hydroxide is always in this reaction. The only thing that changes here are the B and the H plus. So if we know carbonates are base, a Bronsted base is something that accepts a proton, accepts a hydrogen. So whatever carbonate forms, it has to have an additional hydrogen in addition to the base, its starting form, and it has to gain a +1 charge. So our conjugate here is HCO3 minus 1. You've got the H, and you've still got the base here. So our base here is CO3. You still see that CO3 in there. And that plus means that we increase the charge by 1, so we go from a -2 to a -1. So this is how you predict any basic reaction. Take your starting base, add a hydrogen to it, and add a +1 charge to its existing charge. The H2O and the OH minus will always be there. Same thing is true of an acid. If I gave you something like acetic acid, HC2H3O2, and I'm not going to tell you what the reaction is. You should already know how to predict it. Well, acids lose a proton. So we know we're going to have H plus because the general form has it there. Our conjugate base by the general form is the parent acid minus a hydrogen. So we have to lose a hydrogen. And this -1 means that we're going to subtract off a charge. In this case, it starts out neutral. So we end up with the acetate C2H3O2 minus 1. So this is how you predict any acid-base reaction. Memorize the general forms. For the acid form, there's always an H plus of the product. For the base form, there's always an H2O and an OH minus. Whatever acid you're given, the conjugate is just the acid minus a hydrogen. For any base, the conjugate acid is the base plus a hydrogen. Yeah, you're very welcome. As I mentioned to Muhammad earlier, the point of, at this point, the challenge with chemistry is that we're getting away from specific examples and we're getting to more broad examples that we back apply to our specific case. So you can memorize all the acids and bases, but it's much more easier to memorize the general forms and take your specific case and make it look like the general forms. So at this level, the expectation is that you can take this concept and apply it. Instead of having to memorize every acid or base reaction, memorize the two general forms and just work with those. Titration curve problem. Okay. So titration curve problem, full disclaimer, we're only best we can do with titration curves are weak acid, strong base, and strong acid, strong base. And the reason is just practicality. There is a easy Henderson Hasselbach expression for the weak acid, strong base, and then for strong acid, strong base, it's really straightforward how those work. So let's look at the two examples. Let's say we have a weak acid, WA, titrated against a strong base, SB, versus a strong acid, SA, titrated against a strong base, SB. So an example of this, HCl versus NaOH. Example of this, acetic acid, vinegar, HC2H3O2 against sodium hydroxide. Now across both of these, we're going to mark the pH equals 7 line. For a strong acid, strong base titration, this will be the shape of our curve. We always have positive curvature at low pH, negative curvature at high pH, and our equivalence point here is going to have a pH equal to 7. And this is because when you completely react away a strong acid with a strong base, the only thing that remains is a neutral salt. For the weak acid, strong base curve, this will be the shape of our curve. We're going to start with negative curvature, it's going to flip to positive curvature, and then it's going to return to negative curvature. Our equivalence point, VEQ, is actually at a pH greater than 7. And the reason this is true is that when we are at the equivalence point, we have reacted away all of the weak acid. And we are only left with its conjugate base. Well, as the name implies, conjugate base is basic, so our conjugate base is driving the pH up. Half the distance between the equivalence point and 0 is the midpoint. So if we know the volume and equivalence, the midpoint is just half that volume. The midpoint is a very special case, and it comes about from the Henderson-Hasselbach equation. So we get pH equals pKa plus the log of A minus over HA. So Henderson-Hasselbach, the pH equals the pKa plus the log of the concentration of the conjugate base over the parent acid. At this point, we've reacted away half the acid, and that half of the acid has become the conjugate base, so they now are in equal concentrations. So at this point, the pH equals the pKa. So this is how you analyze the titration curve. One, you'll know if it's acidic or basic based on starting pH. So starts at low acidity, it's acidic. If you see these inflections in curvature, it's a weak acid. If you only see positive curvature, it's a strong acid. In terms of useful information, if we know the volume at the equivalence point, we can find the volume at the midpoint, and that'll tell us what the pK is, because the pH at the pH equals the pK at the midpoint by Henderson-Hasselbach. Now, the only other complication here is finding the concentration of the acid. Now, we're going to keep it simple, and we're going to work only with monoprotic acids. I do actually talk about in the notes how to do diprotic and triprotic. They're not actually required to be taught in the course, so mostly I keep them there in case we have your particularly questionable group of students and they want to know. There's the master neutralization formula. The master neutralization formula says the molarity of the acid times the volume of the acid all over the reaction coefficient of the acid equals the molarity of the base times the volume of the base all over the reaction coefficient of the base. Now, if they are 1-to-1, being something like acetic acid, there's only one acidic proton and the sodium hydroxide is basic, one base, then we can say that nu A and nu B are both 1. So this will simplify to MA VA equals MB over VB. Now, again, this is a simplified equation. This is not always true. This statement is always true. We need to look at the reaction. So in terms of an example, let me bring up one of the web assigned homeworks. And I know that the text on here is going to be hard for you to see on your computers, particularly at post live streams, but you can at least see the titration curve. So for this particular problem, I just need to clean up my graph really quick, just a minute. We have that at 27.50 milliliters. We're at the equivalence point, the pH is 9.37. The midpoint here has a pH of 5.70. Now the information you're given the bottom left part of the screen, which you probably can't see on yours, the concentration of the base is 0.200 molar. And the volume of the acid, which is also given to you, is 22 milliliters. So let's talk about how to solve this problem. Now, what it's asking you for is the molarity of the acid, the volume at the equivalence point, sorry, I'm going to have to erase this, the volume at the midpoint, the pKa, I think it also asks you for the Ka. No, it definitely doesn't ask you for the Ka. So it wants the molarity of the acid, the volume of the equivalence, the volume of the midpoint, and the pKa. Now, molarity of the acid we'll get to. The volume of the equivalence point is this point here, the 27.50. The volume at the midpoint is just half this number. So 13.75 mLs. And it's always going to be 1/2 that number. The pKa is just the pH at the midpoint, so it says 5.70. The molarity of the acid, this comes from our simplified master neutralization formula. So molarity of the acid is what we're solving for. The volume of the acid was given, it's 22 milliliters. The molarity of the base was given as 0.2. Your volume of base is how much volume it took to react it all away. So this is going to be your volume at the equivalence point, VEQ. So you got the volume of the equivalence point, you know the molarity of the base, the volume of acid was given to you. From there you can solve for the molarity of the acid. This 9.37 is just useless information. It's there to make sure that you actually understand what you're doing. If you don't, you're going to randomly try to grab for numbers in hopes that something works out. But that 9.37 is just distractor information. It doesn't give you anything useful. It was not in a practical sense. So that was a bit fast. Did it help you out? Good. If you're curious, and I'll just show it to you just until somebody asks another question. This is for a monoprotic acid. This is what I would love to set up to do in the lab one semester, and I'm still trying to debate how to practically do this. All right, nice seeing you, Elijah. If we have a diprotic acid, so let's say we have something like H2SO3, sulfurous acid, and we titrate, we'll actually get this. So we'll end up getting two slope. We'll end up getting two plateaus. Now, the furthest out point is the equivalence point. So this is the point where we have neutralized both protons. First one is the first equivalence point where we've reacted away the first proton on that H2SO3. In this region, it's the H2SO3 bisulfite combination that's controlling the pH. In this region, it's bisulfite and the sulfite pH control. Now, when we just had a monoprotic acid titration, we said that at the midpoint, pH equals pKa. That's true. This is pKa 1. So this is the acid dissociation constant for the first hydrogen. Up here, we get the second acid dissociation constant. For a triprotic acid, we just add another hump and we get a third. The reason why we don't really talk about these too much, one, this one's pretty obvious. Here, finding the halfway point can be a bit more problematic just because you've got to estimate now between two steep slopes. The other is that this is the only one that's guaranteed to be acidic. So you see this with bicarbonate, HCO3. HCO3, even though it has an extra hydrogen and does dissociate to form carbonate, CO3 minus 2, it's actually basic. Baking soda makes solutions basic. So this may actually be under basic conditions. There's no way to guarantee it. So it just makes the analysis a bit more complicated. All right, we got a few minutes left. Any questions? Again, diprotic, triprotic won't be on the exam. I think they're very interesting. I would love to put together a lab where you actually do the diprotic and triprotic titrations and see those. Maybe something out for spring of next year. All right, so we'll wrap up today. Lab today, 2 to 5. I'll be available via email or Teams, so feel free to ask me any questions you might have. Your exam is Monday, so there will not be a live stream Monday, but I will be around during that time via Teams and email if you have any type of questions. Particularly email me if you have any issues with the exam pretty quickly. I will try to be available for that. Next week, we start with the material. So we're going to start on redox in electrochem. That is the hardest material we will cover before the final. And I assure you, nuclear chemistry is one of those things that we can definitely pop off in like a day, or that you can definitely teach yourself in a day. So I'll see you all next Wednesday. Thanks for showing up, and I'll see y'all later.